Our sun is big, really big. You could take about 1 million Earths, pack them all together, and they'd still fit inside it with room to spare. It lights up our entire world. It keeps every living thing on this planet alive. And for most of us, it feels like the biggest, most powerful thing there could ever possibly be. But here's something that might surprise you. Our sun is a star. The exact same kind of thing as those tiny little dots you see sprinkled across the night sky. They only look small because they're so unimaginably far away. Our sun just happens to be the one star close enough for us to feel its heat. And here's the part nobody really tells you. Compared to what else is out there, our sun is small. Almost embarrassingly small. It's a spark, a flicker, a candle sitting in a room full of bonfires, because 640 light years from where you're sitting right now, there's a monster called Betelgeuse. A star so enormous that if you pulled our sun out of the sky and dropped this thing in its place, it would swallow Mercury whole, then Venus, then Earth, then Mars, and it still wouldn't be done. Betelgeuse is more than 700 times wider than our sun. It's one of the largest known stars in the entire galaxy. And right now, as you're hearing this, it is dying. Tonight, we're going to find out how it got so big, why it's falling apart, and what's going to happen when it finally explodes. RSA. To understand how big Betelgeuse actually is, you first have to understand what kind of star it is. Because not all stars are the same. Our sun is what astronomers call a main sequence star. It burns hydrogen in its core steadily and efficiently, and it's been doing that for about 4.6 billion years. It'll keep doing it for another 5 billion or so. It's stable, it's predictable. It's the kind of star that gives you time to evolve complex life on a nearby planet. Betelgeuse is not that kind of star. Betelgeuse is a red supergiant. That classification alone tells you several things immediately. It tells you the star is enormous, far larger than anything on the main sequence. It tells you the star is cool on its surface, because red means lower temperature in stellar physics, and it tells you the star is dying, because no star becomes a red supergiant unless it has already exhausted the primary fuel supply in its core and begun a process of structural collapse that will eventually end in catastrophe. But let's put hard numbers on it, because the numbers are where this gets genuinely difficult to process. The sun has a diameter of about 1.4 million kilometers. If you lined up Earths side by side across the sun's face, you'd need roughly 109 of them. The volume is even harder to grasp. You could fit approximately 3 million Earths inside the sun if you packed them in. By every human standard of measurement, the sun is enormous. It accounts for 99.86% of all the mass in the entire solar system. Everything else, every planet, every moon, every asteroid, every grain of dust, all of it combined makes up the remaining 0.14%. Betelgeuse has a diameter roughly 700 times that of the sun. Different measurement techniques give slightly different numbers, ranging from about 640 to 760 solar radii, depending on the study, the wavelength observed, and the time of observation. But 700 is a reasonable middle estimate and the one most commonly cited. That translates to approximately 980 million kilometers across, just under 1 billion kilometers from one edge of this star to the other. Here is what that means in terms of our solar system. Mercury orbits the Sun at an average distance of about 58 million kilometers. Venus orbits at about 108 million, Earth at 150 million, Mars at 228 million. If you place Betelgeuse where the Sun currently sits, its surface would extend outward to somewhere between the orbits of Mars and Jupiter. The exact boundary is difficult to pin down because Betelgeuse does not have a hard surface the way a planet does. It's a ball of gas, and its outermost layers are tenuous, gradually thinning into the surrounding space. But by any reasonable definition of where the star ends, Mercury, Venus, Earth, and Mars would all be inside it. The entire inner solar system would be submerged within a single stellar object. The volume comparison is even more staggering. Volume scales with the cube of the radius. So a star 700 times wider than the Sun doesn't contain 700 times more space inside it. It contains roughly 700 cubed times more space, which is about 343 million times the volume of the Sun. You could fit 343 million suns inside Betelgeuse, and since you can fit 1.3 million Earths inside the Sun, the number of Earths that would fit inside Betelgeuse is somewhere in the neighborhood of 450 trillion. That number has no intuitive meaning. The human brain cannot process quantities that large in any meaningful way, but it's real. It's the actual physical volume of this star. Now, here's something that surprises a lot of people. Despite being 700 times wider than the Sun, Betelgeuse is only about 15 to 20 times more massive. That seems impossible at first. How can something be 700 times larger but only 15 to 20 times heavier? The answer is density. Betelgeuse is extraordinarily diffuse. Its outer layers are spread so thin that they barely qualify as a gas by terrestrial standards. The average density of Betelgeuse's envelope is lower than the best vacuum we can create in a laboratory on Earth. If you could scoop up a cubic meter of material from the outer regions of Betelgeuse, it would weigh less than the air in a typical room on our planet. This is a direct consequence of what's happening inside the star. The core is contracting and heating up as it burns through heavier and heavier elements. And that contraction releases enormous amounts of energy that push the outer layers outward. The star is inflating, except the inflation has been happening for hundreds of thousands of years. The result is a star with a tiny, incredibly dense core surrounded by an impossibly vast, almost empty envelope of hot gas stretching out to nearly 1 billion kilometers. So how do we actually know any of this? How can astronomers determine the width of a star that sits 640 light-years away? The primary method is interferometry. A single telescope, no matter how large, cannot directly resolve the disk of a distant star. Stars are simply too far away and too small in angular terms. But if you combine the light from 2 or more telescopes separated by a significant distance, you can achieve an angular resolution far greater than any single telescope could manage alone. This technique has been applied to Betelgeuse multiple times, most notably by the Very Large Telescope Interferometer in Chile, which has directly measured the angular diameter of Betelgeuse's disk on the sky. The measurement comes out to roughly 42 to 44 milliarcseconds, depending on the wavelength. A milliarcsecond is 1,000th of 1 arcsecond, and 1 arcsecond is 1/3600th of a degree. For comparison, the full moon on the sky is about 1,800 arcseconds across. Betelgeuse's disk is roughly 43,000 times smaller than the full moon in angular terms. And yet, that's large enough to measure with modern interferometry. Betelgeuse is actually one of the very few stars whose surface has been directly imaged, not just as a point of light, but as an actual resolved disk showing surface features. Once you have the angular diameter and you know the distance, calculating the physical size is straightforward trigonometry. The distance to Betelgeuse has been measured by the Hipparcos satellite at roughly 640 light-years, though there is some uncertainty in this number. A 2017 study using radio observations from the E. Merlin array revised the estimate slightly, and ongoing work continues to refine it. But at approximately 640 light-years, a 44 milliarcsecond disk translates to a physical diameter of about 700 times that of the Sun. There's a second independent method that confirms this. It uses the Stefan-Boltzmann law, which relates a star's luminosity to its surface temperature and surface area. We can measure Betelgeuse's total luminosity, which is roughly 100,000 times that of the Sun. We can also measure its surface temperature from its color spectrum, which comes in at about 3,500 Kelvin. The Sun's surface is about 5,800 Kelvin. Betelgeuse is significantly cooler than the Sun, yet it's 100,000 times more luminous. The only way a cooler star can be that much brighter is if it has an enormously larger surface area radiating that light. When you solve the equation for the radius that would produce 100,000 solar luminosities at 3,500 Kelvin, you get a value consistent with the interferometric measurement. Around 700 solar radii, two completely independent methods, one geometric and one physical, arriving at the same answer. That's how we know the number is reliable, but Betelgeuse doesn't sit still. At 700 solar radii, the star pulsates. Its surface moves inward and outward on semi-regular cycles, primarily with periods of about 400 days and about 2,200 days. During these cycles, the brightness changes, the color shifts slightly, and the physical size fluctuates. The star can be 680 solar radii one year and 720 the next. This is not a stable, well-behaved object. It's a star whose own structure is oscillating, driven by complex interactions between radiation pressure, convection, and gravity in its outer layers. In late 2019 and early 2020, Betelgeuse did something that made international headlines. It dimmed dramatically. Over the span of about 4 months, it went from being one of the 10 brightest stars in the night sky to being noticeably fainter, dropping to about 36% of its normal brightness by February 2020. For the first time in modern astronomical history, a major naked-eye star changed visibly enough that non-astronomers were noticing and asking whether it was about to explode. The event became known as the Great Dimming, and it triggered a wave of observations across every wavelength from radio to ultraviolet. The question was simple. Was this the beginning of the end? Was Betelgeuse entering the final collapse before a supernova? It was not, at least not in the way people feared. The most widely accepted explanation is a two-part event. First, a massive convective upwelling, a bubble of superheated plasma, rose from deep within the star and erupted through surface, ejecting a large clump of material outward into space. This is something Betelgeuse does regularly on a smaller scale. Its surface is dominated by enormous convection cells, far larger than anything on the Sun, and material is constantly being lofted off the surface. But this particular ejection was unusually large. Estimates suggest the star expelled roughly 2 times the mass of our Moon in a single event. That material, once ejected and no longer heated by the stellar surface, cooled rapidly. As it cooled, heavier elements condensed into microscopic dust grains. And that newly formed dust cloud, still close to the star and directly in our line of sight, absorbed and scattered the visible light coming from Betelgeuse's surface, causing the dramatic dimming we observed from Earth. The star didn't get physically fainter. It got obscured. The light was still being produced at the same rate, but a significant portion of it was being intercepted before it could reach us. This event was scientifically valuable precisely because it wasn't a supernova precursor. It was a demonstration of how unstable Betelgeuse's outer layers really are. A star that can eject moon masses of material in a single convective eruption is a star whose envelope is barely bound. The gravity holding those outer layers in place is fighting a losing battle against the radiation pressure and convective energy pushing outward. Material is escaping. The star is losing itself into space. Piece by piece, the dust produced by these ejections accumulates in the space surrounding Betelgeuse, forming what's called a circumstellar envelope. Infrared observations have revealed that this envelope extends out to enormous distances, containing the debris of thousands or millions of years of mass loss. Betelgeuse is estimated to be losing mass at a rate of about 1 solar mass every 10,000 to 100,000 years. That sounds slow. But over the star's remaining lifetime, measured in tens of thousands of years at most, it means a significant fraction of its outer layers will be gone before the final collapse even begins. This matters because when Betelgeuse does eventually explode, the supernova shockwave will slam into this pre-existing shell of ejected material. The interaction between the explosion and the circumstellar medium will shape what the supernova looks like, how bright it gets, and how long it stays visible. All of which brings us back to the fundamental question. If Betelgeuse is this large, this unstable, this far along in its evolution, what exactly is happening inside its core that's driving all of this? The answer involves a process unique to the most massive stars in the universe, a process that, once it reaches its final stage, gives the star less than a single day to live. The answer to why Betelgeuse is falling apart starts at its center, in a core so hot and so dense that the physics happening there bears almost no resemblance to anything we experience in ordinary life. Every star is a battle. On one side, gravity is trying to crush the star inward, pulling every atom toward the center. On the other side, energy generated by nuclear fusion pushes outward, creating pressure that resists the collapse. As long as those two forces are in balance, the star holds its shape. The moment fusion stops, gravity wins. And when gravity wins inside a star this massive, the result is one of the most violent events in the known universe. For most of its life, Betelgeuse burned hydrogen. That's the simplest and most efficient form of nuclear fusion. 4 hydrogen atoms fuse together to form 1 helium atom. And the tiny difference in mass between the inputs and the output gets converted into energy according to Einstein's equation. This is the same process that powers our sun, and it's the same process that powered Betelgeuse for millions of years. But Betelgeuse burned through its hydrogen supply far faster than our sun ever will. The reason comes down to mass. Betelgeuse is roughly 15 to 20 times more massive than the sun, and the rate at which a star burns fuel is not proportional to its mass. It's exponential. A star with 15 times the sun's mass doesn't burn fuel 15 times faster, it burns it thousands of times faster. The gravitational pressure at the core of a massive star is so extreme that the fusion reactions have to run at a furious pace just to generate enough outward pressure to prevent collapse. Our sun will burn hydrogen for about 10 billion years total. Betelgeuse, with far more fuel but burning it at a vastly higher rate, exhausted its hydrogen supply in roughly 8 to 10 million years. On cosmic timescales, that's almost nothing. Dinosaurs went extinct 66 million years ago. Betelgeuse didn't even exist yet when the asteroid hit. Once the hydrogen in the core was gone, the core contracted. Without fusion holding it up, gravity squeezed it smaller and denser, which made it hotter. And once it got hot enough, a new reaction ignited. Helium fusion. 3 helium atoms smashing together to form carbon, and in some cases carbon and helium combining to form oxygen. This process is less efficient than hydrogen fusion. It produces less energy per reaction, and the star has to burn through it faster to maintain equilibrium. The helium phase lasts a fraction of the time the hydrogen phase did, perhaps 1 million years. And this is where the story starts to accelerate. When the helium runs out, the core contracts again, gets hotter again, and ignites the next fuel, carbon. Carbon fuses into neon, sodium, and magnesium. This phase lasts roughly 1,000 years. After carbon, neon burns. Neon fusion lasts about 1 year. Then oxygen ignites. Oxygen fusion lasts a few months. Each successive fuel is heavier, less efficient, and burns for a drastically shorter period of time. The star at this stage develops a structure like an onion. layers of different elements nested inside one another, each one representing a completed stage of fusion. The outermost layer is still hydrogen. Below that, helium, then carbon, then neon, then oxygen. And at the very center, the final product of all these reactions is accumulating in a growing ball that represents the end of the line. That final product is iron. Iron is where stellar fusion hits a wall. Every element lighter than iron releases energy when it fuses. That energy is what keeps the star alive. But iron is different. Fusing iron doesn't release energy, it absorbs it. Attempting to fuse iron would take energy away from the core rather than adding to it. It would be like trying to keep a fire burning by throwing water on it. The physics simply doesn't work. So the iron just sits there. It accumulates at the center of the star, growing heavier and denser with every passing day as the silicon layer above it continues fusing and dropping more iron ash onto the pile. The core gets more massive, the pressure builds, and gravity keeps squeezing. The silicon burning phase, the very last stage of fusion in a massive star, lasts approximately 1 day, 24 hours. After millions of years of hydrogen burning, after thousands of years of carbon burning, after months of oxygen burning, the final act takes a single day. The star has been alive for roughly 10 million years, and in its final 24 hours, it builds the iron core that will destroy it. Once that iron core reaches approximately 1.4 solar masses, a threshold known as the Chandrasekhar limit, electron degeneracy pressure can no longer support it against gravitational collapse. The core has been holding itself up through the quantum mechanical resistance of electrons being squeezed too close together. But at 1.4 solar masses, gravity overwhelms even that. The core collapses. And when it collapses, it doesn't fall slowly. It falls at roughly a quarter of the speed of light. The inner core, which is about the size of Earth at this point, compresses down to a sphere, roughly 20 kilometers across, in less than a second. Protons and electrons are forced together to form neutrons, releasing a flood of neutrinos so intense that for a brief moment, the collapsing core radiates more energy in neutrinos than all the stars in the observable universe are radiating in light. Combined, the outer layers of the star are still falling inward. They don't know the core has collapsed yet, because the information can't travel faster than the speed of sound in the stellar material. So an enormous mass of gas, the equivalent of several solar masses, comes crashing down onto a neutron star that is now only 20 kilometers wide. It hits that surface and bounces. The rebound, assisted by the flood of neutrinos and the intense heating of the infalling material, drives a shock wave outward through the star at tens of thousands of kilometers per second. That shock wave tears the star apart. This is a core collapse supernova. Specifically, for a star of Betelgeuse's mass, it would be classified as a Type II supernova. The energy released is on the order of 10 to the 46th joules. For context, our Sun will produce about 10 to the 43rd joules over its entire 10 billion year lifetime. A supernova releases 1,000 times more energy in a few seconds than the Sun will produce in 10 billion years. At peak brightness, a supernova can outshine its entire host galaxy. A single exploding star, brighter than 200 billion stars combined. That is the fate waiting for Betelgeuse. So what would this look like from Earth when it happens? Betelgeuse is 640 light-years away. That's close by galactic standards, but far enough that we are in no physical danger from the explosion. The neutrino flux would pass through the Earth harmlessly. The radiation would be almost entirely absorbed by the interstellar medium and our atmosphere long before it could do any damage. The supernova remnant, the expanding shell of debris, would take tens of thousands of years to reach our neighborhood, and by then it would be so diffuse as to be undetectable. But visually, it would be extraordinary. At 640 light-years, Betelgeuse's supernova would likely reach an apparent magnitude somewhere between -11 and -13. The full moon is magnitude -12.7. That means Betelgeuse's explosion would be roughly as bright as the full moon, concentrated into a single point of light. You would be able to read a book by it at night. It would cast shadows. It would be visible in broad daylight, a brilliant point of light hanging in the daytime sky for weeks or months. Over the following months, it would gradually fade. The point of light would dim, and eventually a faint nebula would become visible in its place, a ghostly expanding shell of gas lit from within by the dying glow of the explosion. That nebula would remain visible in telescopes for thousands of years, slowly expanding and cooling, seeding the surrounding space with heavy elements that would eventually become part of new stars, new planets, and possibly new life. The timeline for when this happens is the part that frustrates everyone. We know Betelgeuse is in the final phase of its life. We know it's burning silicon, or very close to it. But final phase in stellar terms could mean tomorrow, or it could mean 100,000 years from now. We have no way to directly observe what's happening in the core. The neutrino flux from silicon burning would be detectable by current instruments if it were happening right now, but we haven't detected it, which suggests the star may still be in the oxygen or neon burning phase. Each of those phases last months to years, not the single day of silicon burning. That the honest answer is that nobody knows exactly when. It could happen during our lifetimes. It could happen long after everyone currently alive is gone. What we know for certain is that it will happen, and that by astronomical standards, it's imminent. There's one more thing worth considering. The light we see from Betelgeuse tonight left the star 640 years ago. Whatever we're observing now is 640 years out of date. If Betelgeuse exploded yesterday, we wouldn't know about it for another 640 years. And if it exploded 639 years ago, the light from that explosion is already on its way to us right now, crossing the final stretch of interstellar space. About to arrive without any warning whatsoever. There is no advance signal. There is no countdown we can watch. One night, we will look up at Orion, and the shoulder will be brighter than we've ever seen it. And that will be the moment we find out that one of the largest and most famous stars in our sky has been dead for 6 centuries. Betelgeuse has been a fixed point in human mythology for thousands of years. The ancient Egyptians associated it with Osiris, the god of the afterlife. Aboriginal Australians built stories around its red color. Medieval Arabic astronomers gave it the name we still use today, derived from a phrase meaning the hand of the central one. Every civilization that has ever looked carefully at the winter sky has noticed this star and assigned it meaning. And every single one of them was watching a star that was already dying. The redness they admired was the sign of a swollen, exhausted giant in its final stages. The brightness they celebrated was the last surge of a star burning through its final reserves. The steadiness they took for granted was an illusion created by the limitations of the human lifespan. On our timescale, Betelgeuse looks permanent. On its own timescale, it's a few heartbeats away from the end. When it goes, it will leave behind either a neutron star, or, if the core is massive enough, a black hole. The outer layers will expand into a supernova remnant that will glow for millennia. And Orion, the constellation that has anchored the winter sky for as long as humans have looked upward, will be missing its shoulder, but the material blasted outward won't disappear. The carbon forged in Betelgeuse's core, the oxygen, the silicon, the iron that triggered the collapse, all of it will be scattered into the interstellar medium. Over millions of years, that material will mix with other gas clouds, collapse under gravity, and form new stars with new planets orbiting them. The heavier elements the ones that can only be created inside massive stars and in the violence of supernovae, will become part of those new worlds. This is not speculation. This is how our own solar system formed. The iron in your blood, the calcium in your bones, the oxygen you are breathing right now, none of it was made by our sun. All of it was forged inside stars that lived and died billions of years before our sun even existed. Every atom in your body heavier than helium was created in the core of a star like Betelgeuse, or in the explosion that ended one. Betelgeuse is not just a dying star. It's a factory in its final shift, assembling the raw materials that will become someone else's world. The violence of its death is not an ending. It's a delivery system, scattering the ingredients for the next generation of planets, and perhaps the next generation of life, across hundreds of light years of empty space, 640 light years away. A star 700 times wider than our sun is holding itself together by the thinnest of margins. Its core is collapsing through element after element, each stage shorter than the last. Its surface is pulsing and shedding mass into the dark. Its days are numbered in a way that no other visible star in our sky can match. And every clear winter night, you can walk outside, look up at Orion, and see it for yourself. A red dot on the hunter's shoulder. Quiet, steady, unremarkable to the untrained eye. But now you know what it is. Thanks for watching, and I'll see you in the next one.